Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. In the last lecture, we have looked into the calculation of capacitance matrix of a three-phase transmission line, and then subsequently we have also looked into one numerical example showing that how to calculate the capacitance matrix of any three-phase transmission line in the basically in the ABC domain. And we have shown that if we know the geometrical configuration of the transmission line as well as the radius of individual line, we can always first calculate the P matrix, and from there we can calculate the C matrix just by inverting it. And once we invert the C matrix, so from there we can find out the capacitance between any two lines as well as the capacitance of any line with respect to the ground. And then consequently, we can also find out the equivalent circuit. But as we can, but then as actually we will see in our subsequent lectures, we really would not need much of that equivalent circuit. I mean, that equivalent circuit is essentially for a kind of, it is basically kind of pictorial representation for our understanding. But for further analysis, what we need is essentially the 3 cross 3 capacitance matrix, and we have already seen that how to calculate that capacitance matrix. Now let us proceed from this point onwards. Now what we have is now essentially is that we have that for QABC is equal to CABC into VABC, right? Now, and where of course it is a 3 cross 1 vector. This is a 3 cross 3 matrix. This is also a 3 cross 1 vector. So again we just note that QABC is basically QA, QB, QC, just for our reminding ourselves. VABC is nothing but VA, VB, VC, and CABC matrix is nothing but CAA minus CAB. We said that CABC matrix, it will be always, and it is an symmetric matrix, and then minus CCA. So these are the vectors and the matrices. Now we note that, now suppose that Q is equal to say Qm sin omega t. We are talking about sinusoidal. So then therefore I is equal to dq dt is equal to omega Qm cosine of omega t Qm sine of omega t plus pi by 2. So in terms of phasor, if I say that Q is let us say Qm by root 2 e to the power j0, I can say that I is omega Qm by root 2 into e to the power j pi by 2. Right, so then therefore I can say that it is basically j omega q, right? So from this representation, so it will be j omega q, because e to the power j pi by 2 would be represented by j, omega is omega, and qm by root 2 into e to the power 0 is q. So it is j omega q. So if I apply this, so then therefore I can say that from this that j omega q ABC is equal to J omega C ABC to V ABC. So this is nothing but I can say that I ABC is equal to J omega C ABC into V ABC. Of course, these are all known relations. We have just again derived it just for our own recollection. So this is, of course, it is already known relation. Now I also know that I can say that IABC is equal to the symmetrical component transformation matrix into I 0 1 2, and VABC can also be written as V 0 1 2, where I 0 1 2 and V 0 1 2 are individually 3 cross 1 vector, and I 0 1 2 is nothing but I 0 I 1 and I 2, that is the 0 sequence, positive sequence and negative sequence. Similarly, V 0 1 2 is 0 sequence, positive sequence, negative sequence, and matrix A is given by this also we know. So 1 1 1 1 is square A and 1 A square. So this we already know, and we just note that it is 1 by 3 A inverse is given by 1 1 1 and then 1 A square 1 square A. So this is the, so now if I, so from here if I can write down A I 0 1 2 is equal to J omega C A B C A V 0 1 2 I 0 1 2 is equal to, now omega is omega is basically a scalar quantity, so I can say that J omega A inverse C A B C into A into V 0 1 2. So I can write it down as J omega C 0 1 2 into V 0 1 2. So where I say that this quantity is C 0 1 2. So this is basically the capacitance 3 cross 3 capacitance matrix in the sequence domain. So we know that C 0 1 2 is nothing but A inverse C A B C into A. So this is the case. So now let's see that what would be. So then therefore C 0 1 2 is C 0 1 2 is A inverse, means 1 by 3 1 1 1, and A inverse is 1 A square. So 1 A square 1 square A, and then C A B C is C A A minus C A B. And then A is A matrix, we put 1 1 1 1, then it should be A square A 1 A square. Alright. Now if I do all this matrix multiplication first, say this into this and then this into this, and then if I do all this matrix multiplication, the final results would come out to be this. I am just writing down the, please, 2 CMO, then it is CS2 CM2 CS1 plus CM1, and this is CS1 plus CM1. This is CSO plus CMO. This is CS2 minus 2CM2, then CS2 plus CM2, then CS1 minus 2CM1, and then it is CSO plus CMO. So where CSO is 1 by 3 CAA, CMO is 1 by 3 CAB, CCA, CS1 is 1 by 3 CAA plus ACBB plus A square CCC, CM1 is equal to 1 by 3 CAA plus A square CBB plus A. Sorry, this is CS2. This is CS2. This is CM1. 1 by 3 CBC plus ACAC plus A square CAB and CM2 1 by 3 CBC plus A square CAC plus ACAB. So please note that here in this case that this A is nothing but one angle 120 degree, but the A at the subscript they do denote the phase. So this we must note down and we must not get confused. So that's how we calculate the capacitance matrix in the sequence domain also. And in case that my transmission line is completely transposed, then we will, as we have already done in the case of calculation of sequence impedance matrices, we have already shown that in case my transmission line is completely transposed, so then therefore in that case all these quantities CS1, CS2, CM1 and CM2, they will turn out to be completely 0. So then therefore this matrix will be in simply a diagonal matrix. So for a completely transposed line, the capacitance matrix also becomes a decoupled matrix, where the zero sequence voltage will only be dependent on the zero sequence current, and similarly the positive sequence voltage will only be dependent on the positive sequence current, as well as the negative sequence voltage would be only dependent on the negative sequence current. So then therefore in case the So therefore, in case the transmission line is completely transposed, all these sequence networks would be decoupled. But usually, no transmission line is completely transposed. In that case, even the sequence network will not be decoupled. So then, therefore, even the zero sequence uh, network will be also have the component of currents from the positive sequence and the negative sequence, and also similarly positive sequence will also have the components from all the sequence, and then similarly negative sequence network also will also have the components of currents from all the sequences. So um, for a non completely transposed line, even going to the sequence domain does not really simplify our calculation process, right. So then therefore, probably it will be always better to continue our calculation in the ABC domain in case my system is completely I mean, in case my system is unbalanced, as well as my transmission lines are not completely transposed, because as we have seen that if my transmission line is not completely transposed, so even in that case my zero sequence impedance matrix also would be a completely coupled matrix. And similarly, you have just now seen that for a non-completely transposed line, the capacitance matrix also would be a coupled matrix. So then, therefore, going to the sequence domain is not really going to simplify our calculation process. Well, now so far we have only discussed about the calculation of capacitances where there is no ground wire is involved. Now let us look into the case that if I am considering a ground wire, then what happens? So, I mean, we are not going to do much of a calculation, we are just going to outline the basic procedure, because I have already seen this basic procedure in the context of our calculation of impedance matrix, just to for our a kind of recollection we are going to doing this. So, then what we are doing is now calculation of capacitance in the presence of ground wire. So, essentially what we are talking about, please note we are only talking about now about the three phase transmission line. So, we are not talking about any general n conductor transmission line, because our ultimate focus is to discuss about the analysis and estimation of three phase unbalanced power network. So, we are only restricting ourselves to the calculation of three phase transmission line. So, suppose I do have a three conductors, phase A, phase B and phase C. So, this is line A, line B, line C, and let us say I do have one ground conductor. So, this is ground, let us say this is ground. So, let us say that this is my phase A, and say this is my ground wire, and so because this is ground, so it is grounded. So, this is A, B, C, and we just say that it is neutral wire, but this neutral wire is also grounded. So, then therefore, it is all the same. So, it is in the presence of ground wire. So, in that case, the my capacitances would be between, say, the CAB. I will also have another capacitance CBC, right, and I will also have another capacitance. So, these are the dots. Say this CAC, I will have a capacitance, and then we will have when capacitance says ECG, sorry, then I will have an capacitance between this and this, then I will have an capacitance between this and this. So you can say that it is CAN, you can say that it is CBN, because this is n conductor, and you can say that is CAN. And we can also talk about as if that I do have an capacitance between ground. So I can say that this is CCG, I can say that is CBG, and I can say CAG. So we have denoted all kind of capacitances existing between any two pairs of the lines. So now here, because this conductor N is grounded, so then therefore you can say that these two capacitances CAN and CAG, CAN, so this would be CCN, I am sorry, this must be CCN, this must be CCN, CCN, CBN, CAN, this is CCG, CBG, CAG, right. So then therefore, as this neutral conductor or other conductor N is grounded, so then therefore, as you can see that CCN and CCG, they are actually in parallel, so then therefore the net capacitance to ground, they will increase. Similarly, the capacitance to ground would be actually the sum total of the capacitances of CBN and CBG, so that will also increase, and as well as the capacitance to ground would be equal to the sum total of CAN and CAG, that will also increase. So these we can understand from our, let us say, basic intuition. Now let us see whether that is really reflected into our calculation or not. So for that, we note that I can write that VA, VB, VC and VN is 0 because it is grounded. So that we can write down P matrix PAA, PAB, PAC, PAN, PBA, PBB, PCA, and PNA. Right, and we know that how to calculate these coefficients, P coefficients, so we are not going to repeat it. Now because it is 0, so then again we can simply partition it. So we do the partition. So then therefore this we can write down that VABC then 0, then let us say that we do this partition, right. So we call this P1 matrix, we call this P1 matrix, we call this P2 matrix or vector, whatever, we call this P3, we call this P4. So P1, P2, P3, P4. Of course, P4 is equal to PNN. is equal to, I can say that it is Q A B C Q N. So then therefore from here, and of course we know that P4 is equal to Pn, and now from here we know that 0 is equal to P3 Q A B C plus say Pn and Qn. So therefore Qn is equal to minus 1 by Pn and P3. This is the matrix QABC. So therefore from this VABC is equal to P1 P2 Qn P1 QABC minus 1 by Pnn P2 P3 QABC. So P1 minus P2 P3 by Pn QABC. So this I can say that it is P to QABC, right? So therefore VABC is equal to P to ABC. Now what is P matrix? P matrix would be, P matrix is P1 minus 1 by Pnn into P2 P3. So 1 by Pnn to P2 P3. So let us do that. So P1 is PAA, PAB, PAC, PBA, PBB, so this is P1 matrix, you see. So this is the P1 matrix, and then P2. P2 is PAN, PBN, PCN. So 1 by PNN minus, so minus 1 by PNN, and then P2. P2 is PAN, PBN, PCN. So it is PAN, PBN, and P3. P3 is PNA, PNB, PNC. PNA, PNA, PNB, PNC. So that is the matrix. So it turns out to be, so now this is PAA, PAB, PAC, PBA, PBC, PBB, PBC, PCA. Minus PAN to PNA by PNN, PAN into PNB by PNN, PAN to PNC by PNN, PBN, PNA by PNM, PBN, So now you see that this is basically this matrix minus this matrix. So you see the overall matrix has now actually basically reduced. Earlier it was this one. Now this actual P matrix is this matrix minus this matrix. So then therefore all the terms of this final P matrix would be reduced as compared to the original values of PA, PAB, PAC, PBN, etc. Right. So then therefore the final values of this P matrix would be actually less than the original values of PA, PAB, PAC, PBA, PBB, PBC, PCA, PCB, PCC, right, because these will be less. So then therefore this P matrix, final P matrix, all the elements of this final P matrix would be less than this P1 matrix. Now, because all the elements of this final P matrix is less than the original P1 matrix, now if we take the inverse of this final P matrix, the values of the capacitance matrix would be higher, because the values of this P matrix would be lower. So, then therefore, when you take the inverse of a matrix which has got lower values of all the elements, the values of the inverted matrix would be higher. So, then therefore, all the values, or rather the absolute values of all the elements of the C matrix would be higher. So, as a result, what will happen? As a result, the value of the capacitance with respect to ground of any node also will be higher, right. So, then therefore, from our intuitive understanding, we have already said, just by drawing the capacitance diagram, we have already deduced that in case I have gotten ground over, so my capacitance to ground would be higher, because it will be actually parallel combination of two capacitances which simply add, and that same thing will also be reflected if we just do follow the calculation process, right. And what would be the final value of these capacitances, etc., etc. So, that means what would be the final value of the capacitance of any phase conductor with respect to ground, that will be given by the inverting this P matrix, right. But then those values would be higher as compared to the case had there been no ground conductor. So, our calculation process also exactly corresponds to our intuitive understanding. So, and again we can follow up, we can do this same calculation process in the presence of more than one ground conductor, etc., etc. But we are not continuing with this. So, we stop with the topic of calculation of capacitances of a transmission line. So, so now from the next lecture onwards, we will start looking into possibly the modeling of transformers. Thank you so much.